Section 10, hydrograph. So what is hydrograph? Hydrograph is record of river discharge over a period of time. And river discharge, we know from previous class, Q equals to area times velocity. The same here we have will be river discharge will be equals to cross-sectional area times river's mean average velocity at a particular point in this course. Storm hydrographs show the change in discharge caused by a period of rainfall. Why I construct and why we have to analyze hydrographs? To find out discharge patterns of a particular drainage basin, help predict flooding events, therefore influence implementation of flood prevention measures. This is why we need hydrographs. So construction of storm flood hydrographs. So you will see hydrograph looks like this one. This is flood hydrograph. In horizontal axis, we have hours from start of rainstorm, and vertical axis we have discharge. It can be in meters cubed per second or feet cubed per second. And again, at the left, as see here, we have in millimeters, that is rainfall, start from 0 to time 12. And at the same time we construct, we have rising limb at the top, basin, lag time, peak flow at the right, recession limb, and we have at the bottom basin flow, through flow, and overland flow. We have to see what are these. So discharge in the vertical axis, it is in meters cubed per second, and the hours, as you see here, is from 0 to 72. So here, this is rainfall in millimeters. As you see here, let's say we had rainfall, and this rainfall shown in millimeters as a bar graph. It can be in inches or millimeters. So if we had a rain, we want to see how we can construct our hydrograph. So the hydrograph looks like this one, the discharge in meters cubed per second as a line graph. And the lift, it is rising limb. Rising limb is the rising flood water in the river. At the top, we have peak flow. Peak flow is maximum discharge in the river, or maximum flow rate. As you see in the curve, that is the maximum point in this curve. That is peak flow. That is our concern in floodplains. And then we have recession limb. Recession limb, falling flood water in the river. And we have basin lag time, as you see here at the top left, the time difference between the peak flow of the rainstorm and the peak flow of the river. So that is between the peak flow of the rainstorm and the peak flow of the river. So at the bottom, again, we have the hours from start of the rain, and left vertical line, we have discharge vertical axis. And here base flow means the normal discharge of the river. And then we have overland flow and through flow, which we call it storm flow. So overland flow plus through flow will be storm flow, as you see in this graph. Overland flow means volume of water reaching the river from surface runoff. That is overland flow. Through flow, volume of water reaching the river through the soil and underlying rock layers, both reaching to the river, but one directly from runoff, another from the rock and the soil. So let's see what is analysis. The factors influencing storm hydrographs are area, shape, slope, rock type, soil, land use, drainage density, precipitation, temperature, and tidal conditions. Here I will go overview of these, and then we will try to solve the problem. So interpretation of storm hydrographs, you need to refer to rising limb, recession limb, lag time, rainfall intensity, and peak flow compared to base flow, and final recovery rate back to base flow. Here are some theoretical interpretations of influencing factors, but when interpreting hydrographs, all factors must be considered together, not just one. Area: larger or large basins receive more precipitation than small, therefore have larger runoff. Larger size means longer lag time, as water has a longer distance to travel to reach the trunk river. Shape: elongated basin will produce a lower peak flow and larger lag time than a circular one of the same size. Slope: channel flow can be faster down a steep slope, therefore steeper rising limb and shorter lag time. Rock type: permeable rocks mean rapid infiltration. So little overland flow, therefore shallow rising limb. Soil infiltration, remember we worked in previous chapters, is greater on thick soil, although less pervious soils, for example clay, act as impermeable layers. Most of the time we use clay as a liner in our projects, but because that is impermeable. The more infiltration occurs, the longer the lag time and shallower the rising limb. Land use: urbanization, concrete. For example, you change your land use from green to concrete, and the concrete will give you impermeable surface, creating steep rising limb and shortening the time lag. Drainage density: a higher density will allow rapid overland flow. Precipitation and temperature: short, intense rainstorms can produce rapid overland flow and steep rising limb. If there have been extreme temperatures, the ground can be hard, causing a rapid surface runoff. Snow on the ground can act as a store, producing a long lag time and shallow rising limb. Tidal conditions, although that's important, high spring tides can block the normal exit for the water, therefore extending the length of the time the river basin takes to return to the basin or to the base flow. So these influencing factors will influence each other, change throughout the river course. Barnes in 1940 showed that the recession of a storage can be expressed as Q equals to Q initial times KR to power T. K initial is the initial discharge and QT is the discharges at a time interval of T days. K is the recession constant of value less than unity. Previous also equation can be expressed as below. As you see here, Q can be Q equals times e to minus a times time, where a equals to minus natural log of k. The recession constant k also can be considered to be made up of three components. So we have three types of storage as k equals to KRS, KRI, KRB. KRS is the recession constant for surface storage. KRI is the recession constant for interflow, and KRB is the recession constant for base flow. So base flow separation: the surface hydrograph is obtained from the total storm hydrograph by separating the quick response flow from the slow response runoff. The base flow is to be deducted from the total storm hydrograph to obtain the surface flow hydrograph in three methods. So here are some methods. First is straight line method. Means you draw a horizontal line from start of runoff to intersection with recession limb. Means point A, that is point A. Then extend from the time of peak to intersect with recession limb using a lag time the n equals to 0.83 times a to power 0.2, where a is the drainage area in kilometers squared and n is days where point B can be located and determined at the end of the direct runoff. So you directly from A, you have straight line from point A to point B. Method 2, in this method, the base flow curve existing prior to the beginning of the surface runoff is extended till it intersects the ordinate at the peak, means point C. So you have direct line from A to C, that's flow curve, and then from C the point is joined to point B by straight line. So how we can point B? From the peak to point B, there is n, and you go back and use previous formula to find what is the n, and again from A to C, from C to B, what is the below ACB will be base flow. Method 3, in this method, the base flow recession curve after the depletion of the flood water is extended backwards till it intersects the ordinate at the point of intersection, means line EF. Line EF. Go back to the right figure, 6.5 base flow separation. Find EF. That will be EF, that's a curve, up to F, and then point A and F are joined by an arbitrary smooth curve. From A to F, we have one curve. From F to B, there will be another curve. There's another method. Also, this method of base flow separation is realistic in situations where the groundwater contributions are significant and reach the stream quickly. So you have groundwater reaches to the river. The selection of any of three methods depends upon the local practice and successful predictions achieved in the past. The surface runoff hydrograph obtained after the base flow separation is also known as direct runoff hydrograph, DRH, direct runoff hydrograph. Effective rainfall. In figure 6.c, as you see here, the hyetograph of the storm, the initial loss and infiltration losses are subtracted from it, so this is just pure storm. The resulting hydrograph, we call it effective rainfall hydrograph, ERH, means the initial loss and infiltration are subtracted from the total storm. The hydrograph of rainfall excesses or supra rainfall. Both DRH and ERH represent the same total quantity but in different units. ERH is usually in centimeters against time, and the area multiplied by the catchment area gives the total volume of the direct runoff, total area of DRH. Problem 9.1, please open your book, page 313, problem 9.1. There is here, as you see in the table, you have time versus flow rate. Means for each time you have flow rate in feet cube per second, CFS, you will find these, and after that, first you have to graph it, and then you will find part A, B, C in this problem statement. You need to find the base flow, you have to graph it, and then you have to find K as groundwater recession constant. So here, the same paper that you see here, try to download from your D2L. You have 3 different PDF files. This is the first one, that is regular paper, and there is another one, it will be semi-log. So after you download it, print it out, and maybe you will need for your exam as well. So here, try to find for each hour what is the flow rate and graph it. Stop here and graph it, and then play the video to see what will be the video. So first I put all of the points here. For each hour, the first one, it is 102. For hour 1, as you see here, it is 102. For hour 2, it is 100. For hour 3, that is 98. Try to just locate the points in the graph that we have here. After you put here, you need to curve it. It cannot be linear. It should be in curve. When you curve, it will looks like this one. So try it in your paper to sketch this one, and then we will go for the next parts. The first is rising limb. A rising limb starts from this point, means 2 hours, and it ends at hour 12. Point A will be at 2 hours. As you see here, this is almost the minimum that hydrograph starts. Point B, you can find point B from the peak point. You need to find N for how many days to point B, or why we pick up 12 hours here. As you see, the curve recession limbs, it is in curve up to hour 12. After hour 12, it is a straight line. Where we switch from curve to straight line, that is point B. So we have peak flow at the top, as you see here. And then here will be inflection point. Inflection point means the curvature of the curve changes. That is inflection point. At the right, again, we have another inflection point. We have, so we call this one crest segment. And then from here, we call at the right recession limb. Now, how we can find your base flow? If you remember, go back to your slides. If you sketch one direct straight line from point A to point B, you can find the flow below will be base flow. Or if you remember, in other sections we had from point A, you can go in curve to below inflection point in recession limb, and then from recession limb you can go one line in the slope of exactly what is it from B to the end. Means from B to the end, that is linear, you have to continue that line. It will intersect at hour 6 below recession limb's inflection point, and from that you need to sketch one curve to A. So whatever it is below this green will be base flow. Now again, there's another paper. Stop the video here. After you download it, try to find the points in semi-log paper. As you see, the time is in hours and flow rate in a discharge and CFS. After you put your points, try to graph it. After you graph, you see that at hour 12, which is our point B, after this point it is linear. So we're trying to find K. K is groundwater recession constant. How we can find K? Or again, I put here, you graph it the whole in CFS from 0 to 15 hours. That is, we have the curve. Groundwater is for linear part, means there is discharge from groundwater to the river. Now we're trying to find that one. K equals to here, which is the linear here. K equals to Q at time over Q initial, which here, as you see here, at time 13, the number is 54. At time 12, that number is 60. If you divide, that will be 0.9. So from 12 to 13, that's 0.9. But if you graph it, I provided you another graph that is regular paper, but in y-axis you have to take natural log, and after you take natural log, you'll find these numbers, and then you will graph it. So means x-axis, that is horizontal line, that is just the time. Y-axis, that is natural log of, you can take log or just natural log, any one you can use. But after if you take, let's say, log, you will find these numbers, and after you find these numbers, the slope will be from, as you see here, for time 12 to time 13, that will be, time 13 is 1.7324 minus, so what we do here, we find the slope. delta y over delta x. Delta y is 1.7324 minus 1.7782, that is delta y, over delta x from 13 to 12, that is 1 hour. So the number will be minus 0.0458, and k, if you use the vertical axis as log, you need to find k equals to 10 to power this number. But if you use natural log, the k will be e to power minus this number. So let's say you use just log. If you use log, it will be 10 to power minus this number that you find the slope, will be 0.9. If you find from 13 to 12 and from 14 to 15, you will find 0.898 and 0.897. And you need to take average. Average is constant. K, almost you can say that's 0.9.